Hi friends, welcome back to engineeringtalks.com. The previous video was about convolutions, right? We saw its definition, its properties, and then we found out the inverse Laplace transform of functions using convolution theorem. In this video, we'll go through the topics second shifting theorem and Laplace transform of unit step function. We have already learned about first shifting theorem. So today, we'll see what this second shifting theorem is, and then we will move into the topic unit step function and solve problems on that. So happy learning, and don't forget to like, share, subscribe the channel and press the bell icon.
Second shifting theorem. We already know what first shifting theorem is, right? What is first shifting theorem? Laplace of e raised to minus at f of t is equal to f of s plus a, and Laplace of e raised to at f of t is equal to f of s minus a. I explained this in the previous videos, so please watch those videos first in order to clarify your doubts. And I'll do one thing, I'll provide the link in the description so that you can easily navigate to that video. Now, according to second shifting theorem, if f of s is the transform of the function f of t, then e raised to minus as f of s, where a greater than 0 is the transform of the function g of t, where g of t is defined by 0 when t less than 0 and f of t minus a when t greater than 0. That is, g of t will be equal to 0 when the value of t becomes less than a, and g of t will be equal to f of t minus a for all values of t greater than a. That is, Laplace of g of t is equal to e raised to minus as f of s. Now let's prove this. Laplace of g of t is given by integral 0 to infinity e raised to minus st g of t dt. We all know this. Now we can split the integral between the limits 0 to a and a to infinity, since it's a piecewise continuous function. Therefore, integral 0 to a e raised to minus st g of t dt plus integral a to infinity e raised to minus st g of t dt. Now, from 0 to a, that is when the value of t is less than a, we'll have the function value equal to 0. So this term becomes 0. Now, when the value of t becomes greater than a, then the function value will be equal to f of t minus a. Therefore, integral a to infinity e raised to minus st f of t minus a dt. Now, let's substitute t minus a with u. Okay. Therefore, t will be equal to u plus a and dt will be equal to du. Now, these limits are in terms of the variable t. Now, since we are changing the variable t to u, we have to change the limits as well. So, when t is equal to a, we'll have u is equal to a minus a, that is 0. And when t is equal to infinity, we'll have u is equal to infinity minus a, that is infinity. So, u is equal to infinity. Therefore, Laplace of g of t is equal to integral 0 to infinity e raised to minus, now in the place of t we'll write a plus u f of u du. Now we'll take e raised to minus as outside since it's a constant. Therefore, e raised to minus as integral 0 to infinity e raised to minus su f of u du. Now this is f of s, right? Therefore, Laplace of g of t will be equal to e raised to minus as f of s. Now let's see what is meant by a unit step function. The unit step function is defined by u subscript a of t, where u subscript a of t is equal to 0. That is, the unit step function value will be equal to 0 if t less than a, and the function value will be equal to 1 if t greater than a for a greater than or equal to 0. Looking at this, we can see that it is similar to the function g of t defined before. G of t is equal to 0 if t less than a, and g of t is equal to f of t minus a if t greater than a, right? The only difference is that in the case of g of t, we have f of t minus a in the place of 1. Therefore, we can rewrite the function g of t as g of t is equal to f of t minus a u subscript a of t. That is, if t less than a, we have the unit step function value equal to 0. Therefore, g of t will be equal to 0. And if t becomes greater than a, we have u subscript a of t equal to 1. Therefore, g of t will be equal to f of t minus a. The results are the same. Therefore, we can rewrite g of t using the unit step function like this. That is f of t minus a u subscript a of t. Now you can denote the unit step function using u subscript a of t or u of t minus a. Therefore, g of t can also be written as f of t minus a u of t minus a. You can use this one or this one according to your convenience. Therefore, Laplace of g of t is equal to Laplace of f of t minus a u of t minus a, which is equal to e raised to minus as f of s. We know that Laplace of g of t is equal to e raised to minus as f of s, right? Therefore, Laplace of f of t minus a u of t minus a also will be equal to e raised to minus as f of s. Now, let's take this L to RHS. Therefore, Laplace inverse of e raised to minus as f of s is equal to f of t minus a u of t minus a. Now let's take the Laplace transform of the unit step function. Laplace of u subscript a of t is equal to Laplace of u of t minus a, which is equal to integral 0 to infinity e raised to minus st f of t dt. Now the function value is equal to 0 when t less than a, right? That is from 0 to a, and the function value is equal to 1 when t greater than a, that is from a to infinity. Therefore, integral 0 to a e raised to minus st into 0 dt plus integral a to infinity e raised to minus st into 1 dt. Now this becomes 0. Now we have only this left. Therefore, integral a to infinity e raised to minus st dt. The integral of e raised to minus st is e raised to minus st by minus s within the limits a to infinity, which is equal to, now we'll take this minus 1 by s outside. Therefore, minus 1 by s into e raised to minus infinity minus e raised to minus as, which is equal to minus 1 by s into e raised to minus infinity is 0 minus e raised to minus as. Now minus becomes plus e raised to as by s for s greater than 0. Now we have Laplace of the unit step function, that is Laplace of u of t minus a is equal to e raised to minus as by s. Now let's find out the inverse Laplace transform of e raised to minus 3s by s minus 1 raised to 4. Look at this function. This is of the form e raised to minus as f of s, right? And here f of s will be equal to 1 by s minus 1 raised to 4. So let's first find out the inverse Laplace transform of 1 by s minus 1 raised to 4 so that we can obtain the function f of t. So Laplace inverse of 1 by s minus 1 raised to 4 is equal to e raised to t Laplace inverse of 1 by s raised to 4, right? That is, look at the denominator, we have s minus 1 here. This s minus 1 is due to e raised to t. So if we take that e raised to t outside, the denominator will become equal to s. If you have any doubt in this, please watch the previous videos. I'll provide the link in the description. So you can go to that video and watch it and clarify your doubts. So Laplace inverse of 1 by s raised to 4 will be equal to t raised to 4 minus 1 by 4 minus 1 factorial. That is, Laplace inverse of 1 by s raised to n is equal to t raised to n minus 1 by n minus 1 factorial. So Laplace inverse of 1 by s raised to 4 will be equal to t raised to 4 minus 1 by 4 minus 1 factorial. That is t cube by 3 factorial. And 3 factorial is equal to 6. Therefore, e raised to t cube by 6. Now Laplace inverse of e raised to minus as f of s is equal to f of t minus a u of t minus a, right? Now here a is equal to 3, e raised to minus 3s, and we have 3 in the place of a. So a is equal to 3. Now we'll substitute f of t with f of t minus a. So e raised to t minus 3 cube by 6 u of t minus 3. So Laplace inverse of e raised to minus as f of s is equal to e raised to t minus 3 cube by 6 u of t minus 3. Let's find out the inverse Laplace transform of e raised to minus 4s by s minus 1 into s minus 2. This is also of the form e raised to minus as f of s with f of s equal to 1 by s minus 1 into s minus 2 and a equal to 4. So before finding out the inverse Laplace transform of 1 by s minus 1 into s minus 2, we'll have to split this into partial fractions. So for splitting this function into partial fractions, we should understand the factors present in the denominator. Here in the denominator, we have non-repeating linear factors. So partial fraction takes the form a by s minus 1 plus b by s minus 2. Now we'll cross multiply and make the denominators equal on both sides of the equation. So a into s minus 2 plus b into s minus 1 by s minus 1 into s minus 2. Now we'll cancel out the denominators and the equation becomes 1 equal to a plus b into s minus 2a minus b. On equating the coefficients of s on both sides of the equation, we'll get 0 equal to a plus b, because on LHS we don't have any s terms. So the coefficient is 0, and on RHS the coefficient of s is a plus b. Therefore a equal to minus b. And on equating the constants on both sides of the equation, we'll get 1 equal to minus 2a minus b. And let's substitute minus b in the place of a, and we'll get minus 2 into minus b, and this becomes equal to plus 2b. Therefore 1 equal to plus 2b minus b, that is b equal to 1. Hence a equal to minus b, which is equal to minus 1. Now let's substitute the constant values. Therefore we'll get Laplace inverse of 1 by s minus 1 into s minus 2 equal to Laplace inverse of minus 1 by s minus 1 plus 1 by s minus 2. Now using the linearity property, we'll split this and write it as Laplace inverse of minus 1 by s minus 1 plus Laplace inverse of 1 by s minus 2. Now we can take this minus outside, and Laplace inverse of 1 by s minus 1 is e raised to t, and Laplace inverse of 1 by s minus 2 is e raised to 2t. Therefore, Laplace inverse of e raised to minus 4s by s minus 1 into s minus 2 will be equal to, we know that Laplace inverse of e raised to as f of s equal to f of t minus a u of t minus a. Here f of t is equal to minus e raised to t plus e raised to 2t. Therefore, f of t minus a will be equal to, here a is 4. So, t minus a will be equal to minus e raised to t minus 4 plus e raised to 2 into t minus 4 u of t minus 4. Please do like and share the video and subscribe the channel. Thank you.